Hello everyone, welcome to Binary Search Tree Part 1 by George Tony AF. I am a senior software engineer at LinkedIn.com and let me go through this. Let's go through the contents of this video. In this video, we are going to speak about what is binary search tree, the Python code for binary search tree, and two of the operations in binary search tree, BST, searching and insertion, and the Python code. However, since this is a large topic, we will only going to go through researching and insertion, while the deletion and traversal will be explained in another video. Since there are multiple cases you have to look through in a deletion case, it requires a video of its own. What is binary search tree? For that, first let's go through what is a binary tree. A binary tree is an abstract data type where a node can have at most two childs. These childs are referred as left child and the right child. And now when it comes to a binary search tree is a specialized case of a binary tree in which internal node is greater than all the keys in the respective left tree, the nodes, and less than all the keys in the respective right subtree nodes. As you can see in the picture, the nodes in the left side are less than the root node 8, and while the values in the right side are greater than the 8. This specific condition is called a binary search tree, and we will be going through this particular tree as an example throughout the video course. So this is the Python code I have written for the binary search tree, or specifically the node, where the node has three values, one value, and the two right child and the left child, and the string representation is given here, and you can see it. The A node is node 5 and A left of node is 4, and print A. This is the output. And this is the representation of binary search tree, where we have a root. Root is a node. So let's deep down into searching in a binary search tree. For this case, we are going to check for finding value of 6 and 9. As you can see, 6 is already present. So let me go through the algorithm. And what we're going to do is, first we're going to compare the value with the root node. Then we will check where we have to navigate first. So let's compare 6 to 8. Since 8 is greater than 6, so we can be sure that the 6 will be located on the left subtree. So we will navigate to 3. And we will compare 3 with 6, and since 3 is less than 6, we will navigate to the right subtree. And we will compare the root again. 6 equals 6, so we will find the node and we return it. So let's check through the next example, that is 9. Since 9 is not present, we should not get the value. So just like earlier, we're gonna check 8. We will compare to 8 to 9, which is not true. So we will, since 8 is less than 9, so we will go through the right. 9 is greater, so we'll go to the right. So we'll compare 10 and equals 9. It's not true, and 10 is less, so we should go to the right, the left part. Since there is no node here, we will return none or false. So I just gave an explanation how we are searching it. Now let's convert that to algorithm and code. As you can see, we are defining method find in the node that is written here. So the condition first we are checking, like we have to check the root value of node, and that is searched here. Self dot value equals value, and if that's true, then return true. That means we found the node we are searching is the root. So what happens when if the node value, the root is less than the value? That's the else case. So we have to go to the left child. That's been checked, and we are checking if the left child exists or not. If it don't, we have to return false, which means that there is no left subtree. So it means that node is not, value is not present in the binary search tree. If its left child is present, then we have to recursively call it for the left node. That is self.left.find value. And if the value is less than value, that means we have to search in the right child or right subtree. This is being written here. If self.right exists, then go to the right and check for value, else false. And this is the part we have to write it for the BST. Here we are just checking find self value. So we are checking if the root is done, the return false. That means there is no that's an empty binary search tree. Else we will find it for the root, which recursively go through the entire subtree. So just that, the example I have shown earlier, I just represented it as a binary search tree. See, node equals node 8 and BST is node, and I have created the subtree. I'm checking the same very example I told you earlier is 6% in the BST dot find 6 and 9, and this is the output. 6 is present while 9 is not. So after finding a node in the binary search tree, it's up to us to insert it. So in the last example, we showed that 9 does not exist in the BS tree, and now we are trying to add it to the BST. So the algorithm is just like finding the node, but there is a difference. So let me go through it. Here we are going to check. We are going to add 9. So since 8 is less than 9, we have to move towards the right subtree, and we are going finding 10. 10 is greater than 9, so we have to move to the left subtree. Here there is no left subtree, so we are going to add it 9 here. And that's how the addition works. Addition is fairly simple. So now we are going through the Python code for that. So in the node part, we are just adding insertion logic. So this is the first part. We are checking the root node. Self.value is less than value, and if self.right is none, that means if it's less, and if right child is not present, then self.right we create a new node and attach it to the binary search to the node. And if right node exists, then we will go through the right subtree to insert that value. That's recursive call. And similarly, if left child is done, we'll just append to the left child, or we will go through the left subtree to find its position. And that's how the node is. For the BST, this is how it's done. For first case will be, we are checking if the root exists or not. If the root is none, then we will create it as the root node. Otherwise, we will go through the root node to insert the value. And this is how it's done. So binary search tree true exists, 9 does not, then we will insert 9, and after that it's true. So here I put a print statement here, print self.value and value. So after that, self.left node is attached. You can see that self.value is 10 and new value is 9. That means it is attached to 9 is left to the 10, just like I explained earlier. So this is a one easy way I just made to make sure that you get what I'm saying. This is little complicated when you go to recursive logics, but it's fairly easy to write the code once you understand how the recursion works. As I told you earlier, this is a fairly big concept for binary search tree. There are a lot of algorithms there. For example, what's next is the traversal and deletion. And deletion has multiple cases. So if a root node is the one to delete and there is a tree left tree and subtree, then we have a different logic to apply. So, and traversal, there are three types of traversal: pre-order, in-order, and post-order. So this requires another video. This is entirely a 10-minute long video, and it might even go further, and that will actually bore you a lot. So let me just cut short this one, and so that you can have, I'll create a part 2 video and you can learn from there.